We've studied ideals in commutative rings extensively. We need to be a little more careful while studying ideals in non-commutative rings. The slight complication arises because multiplication doesn't commute, and there are two different flavors of ideals. There are left ideals and right ideals. So a left ideal is just additive subgroup of R. So it's a subset of R that is closed under addition, contains 0 and has additive inverses. So this part is the same as in the definition of the ideal, but the additional condition is that Rx belongs to I for all x in I and R in R. Now this condition looks exactly the same as the definition of an ideal in a commutative ring, but there's a different variant of this where we will put the R on the right. So a right ideal again is an additive subgroup of R. Such that XR belongs to I for all x in I and R in R. And then finally we have the notion of a two-sided ideal. A two-sided ideal is just an ideal which is a left ideal and a right ideal. In a commutative ring, these three notions all coincide. Left ideals are the same as right ideals and they are all two-sided ideals. Let R be the ring of n by n matrices. I'll just call it M and K. All n by n matrices with entries in a field K. So we assume that K is a field. And R forms a ring under matrix addition and matrix multiplication. So now for a matrix A in R, I'll use the following notation. Aij denotes the element in the ith row, the entry in the ith row and jth column of R. The ijth entry of A. And I'll use Ai star to denote the ith row of A. So you think of it as a row vector. And A star j will be the jth column of A. Column vector. And I'll use the notation R of A to denote the row space of A. So that's the span of Ai star. I goes between 1 and n. And similarly C of A will be used to denote the column space of A. That is span of A star j 1 less than or equal to j less than or equal to n. Now we'll try to figure out what are the left ideals, the right ideals and the two-sided ideals in R. So firstly, let me give you a construction of some left ideals and right ideals. So let V be any subspace of k to the n, and then we can define two subsets of R. We'll define R of V to be those matrices A such that row space of A is contained in V, and we'll define C of V to be those matrices A in R such that column space of A is contained in V. Okay, now recall an important fact from linear algebra, that the row space of AB is contained in the row space of B, and the column space of AB is contained in the column space of A. So what this means is that if you take any matrix whose row space is contained in V and you multiply it on the left by another matrix, then the product matrix will still have row space contained in V. So that means that this is a left ideal And here, if you have a matrix whose column space is contained in V and you multiply it on the right by another matrix, then the column space of the product is still contained in V. So that means that this is a right ideal. It turns out that these are all the left and right ideals of R. How do we see that? So to see that, we need to given an left ideal, let's do it for left ideals. So given I in R, a left ideal, we need to identify the subspace V for which this ideal I is of the form RV. So how would we get that subspace V? Well, an obvious choice, if you think about it a bit, is to let V be the span of the row spaces of all the matrices in I. So you take all A in I and you take all I between 1 and n. Okay, so this is of course a huge infinite set usually, but it's going to be a subspace of k to the n. It's going to be a finite dimensional vector space, and it's going to be spanned by a finite set of such rows. Okay, and now what I want to show is that I is actually equal to R of V. Okay, so firstly, if you have a vector, if you have a matrix A in I, then of course the row space of A is going to be contained in V. So because that's one of the matrices whose rows span V. So if A belongs to I, then row space of A is contained in V, which implies that A belongs to RV. So what this says is that I is contained in RV. What we need to show is that the other inclusion is true, that RV is contained in I. Okay, so suppose A belongs to RV. Then each row of A, so in particular row space of A is contained in V, and which means that each row of A lies in V. Okay, so that means that if I take the ith row of V, A I star, I can write it as a linear combination of rows of matrices which lie in I. So I can write this in the form J goes from 1 to K, I goes from, let's say L goes from 1 to N, B J I L A I star J. So this is just what it means to say that AI star is in the span of the rows of matrices in I, where these A1, A2 up to AK belong to I. Okay, but if you think about what this means, this is the same as saying that A itself is summation j goes from 1 to k bj aj, where bj is the matrix whose ith entry is bjil. Okay, now if you look at this equation here, A is equal to summation bj aj, it's exactly saying that A lies in the left ideal lies in the left ideal containing a1, a2 up to al, which means that A lies in I. So what we proved is that RV is contained in I, and so RV is equal to I. So this shows that every left ideal in R is of the form RV for some vector subspace V of Kn. And a similar reasoning using columns instead of rows will show that every right ideal is of the form CV for some subspace V of K to the n. What about two-sided ideals in R? So suppose I is a two-sided ideal in R. Okay, then I is of course going to be of the form C of V for some subspace V in Kn. Okay, now consider two cases. Firstly, if V is the zero-dimensional subspace, so if V is just the subspace consisting of the single vector 0, then of course I is 0 itself, consists only of the 0 matrix just by the definition of CV. Now if V is not 0, then take some non-zero vector V in V. Okay, and now let's look at the matrix AJ, the matrix whose jth row is V, not capital V, is the vector V, and all other rows are 0. So this matrix AJ looks like something like this. In the jth row, we have the vector V, and everywhere else we have 0. So now I ask you, what is the row space of AJ? The row space of AJ is the subspace spanned by the rows of A. At least one of these coordinates in V is non-zero, and so the row space of AJ is going to be the jth coordinate line. So this means that okay, so firstly AJ belongs to I for all j between 1 and n, just because the column space of AJ is contained in the subspace capital V. But on the other hand, the span of AJ I star 1 less than or equal to I less than or equal to n is all of k to the n, because it contains each of the coordinate lines. So that means that by the argument that we had earlier, right, when you have a left ideal, it is R of V, where V is the space spanned by the rows of all the matrices in that ideal. So that means I is equal to C of k to the n, which is all of mn k. That is all of R. So what we have seen here is that there are only two-sided ideals in R, namely the ideal consisting only of the zero matrix, and the other one is the ideal consisting of all matrices in R. Let Q be a quiver. So it's of the form V, E, S, T, where V is the set of vertices, E is the set of edges, S is the source function, tells you where each edge starts, and T is the target function, tells you where each edge ends. And the path algebra, if you remember, this is, as a vector space, it's spanned by all the paths in Q. Now I'll give you some examples of left ideals, right ideals, and two-sided ideals in KQ. So fix a subset S of V, and you define I of S to be the span of all paths with source in S. So this is span of paths P in E star such that source of P belongs to S. And similarly, I define J of S to be span of all paths that end in S. This is span of P in E star such that T of P belongs to S. I claim that this is a left ideal, IS is a left ideal in KQ, and this is a right ideal in KQ. And if you want an example of a two-sided ideal in KQ, you just define N of S to be span of all paths of length greater than 0. All paths of positive length. Remember, the path algebra, the set of paths also consists of paths of length 0, one for each vertex of the quiver. Now if you look at the span of paths of positive length, you can show that they form a two-sided ideal. You should try to prove these three assertions about left ideals, right ideals, and two-sided ideals in the path algebra of a quiver.